Hello, welcome to a review lecture. The topics for this review are going to be the extreme value theorem, first of all, then antiderivatives, initial value problems, and then a little bit of L'Hopital's rule. The goal for today is just to do examples of each one of these examples, showcasing basically everything that can happen. Now, in the topic of the extreme value theorem, these are the same 4 boxes that I already presented in lecture or recitation, I don't remember. You can pause the video right now to be reminded of all of this, but I'm not gonna talk about any of this specifically. The topic of extreme value theorem is this topic of locating critical points and as well as endpoints of the domain, so that you can identify where a function reaches the absolute minimum and maximum values, if it does. So let's move on to an example. Find the critical points and max min values of this particular function in the domain from -2 to 2. By the way, you're going to see this guy a lot, the cube root of x squared, or things equivalent to this, like an odd root of an even power. Essentially because this is the easiest way to create a function that does sharp corner kind of thing around 0. So you can have examples where the critical points happen in a location where the function is not differentiable, and not only a location where the derivative is 0. So it happens a lot in examples. So anyway, we have a function, we have the domain, we want to find the critical points and then the maximum values. Let's find critical points. That means locations where the derivative does not exist or where it is 0. So try to compute this derivative. Writing this first part right here as x to the 2/3 is going to be easier for you. So you're going to need a product rule between this term and the 4 minus x squared term. I'm not going to do this whole calculation here. By this point, we should all have enough practice with derivatives. I'm just going to tell you that in the end, after you factor everything, maintaining powers of x like this, fractional powers, you're going to find this particular expression. 8/3 x to the -1/3 minus x to the 5/3. So this is the derivative. Now we can start analyzing critical points. Where does it not exist? What is the only problematic point in this formula? Well, because you have x through a negative power, if x is 0, that means you're dividing by it by 0, so that's a problem. This formula does not apply at x equals 0. And this is always going to happen when you have an expression like this, like x to the some fraction with an even power up there, so that it's also defined for negative numbers. But then this is 0 is always a problem for the derivative. So 0 is a critical point. But then you can also have f prime of x equals 0 at a few points. Let's solve this equation. So this is what it looks like. Forget about the 8/3 part. Set this equal to 0. How do you solve for x in here? The easiest way is probably to multiply by x to the 1/3. That's going to make the multiply by x to the 1/3 here. That's going to make the first term equal to 1. And then in the second term, you're adding a power of 1/3 to another 5/3. That makes 6/3, which is 2. So now it's much easier to recognize this equation is just x squared equals 1. So x is plus or minus 1. And both of these guys actually belong in the domain that we are considering for the function, which is from -2 to 2. So they are also critical points. Going back here, 1 and -1 is also a critical point. Those are the 3 critical points. Now, how do we finish the question? Find the max and min values. What we have to do is verify every single location where that can happen, which is the critical points and the 2 endpoints, -2 and 2. So you have to find the value of the function at each one of those numbers. F of -2, f of -1, 0, 1, and 2. And just see what the value of the function is at each one. So for example, -2. What happens when you plug in -2 here? Forget about the x to the 2/3 part, the initial part here. The 4 minus x term, minus x squared term is going to be 0. And actually the same thing happens at x equals plus 2. So those are zeros. Now similarly, f of 0 is 0 because of the x to the 2/3 part. And what is f of 1? That part is the 1, and then you have 4 minus 1 here, that's 3. And similarly, f of minus 1 is also 3. You only have x squared in the function, you don't have x. So both minus 1 and 1 will give you the same value. These are the values of the function, 0s and 3s. The largest and smallest of these guys are going to be the global max and global min, which, by the way, we know exist because this is a continuous function over a closed interval. So we know max and min must exist. It must be one of these guys. So 3 is global max value, if you want to say, and 0 is global minimal value. It's important to mention, by the way, it's not just because we found these guys, it has to be one of them. Only if it exists. Sometimes the global min and max does not exist, but the extreme value theorem tells us that in this case it does exist. Continuous function on closed interval. So that's how we know. Moving on. This time it's a piecewise function. It's the same problem. Find the critical points and max min values over this domain. This time let me actually write down, because of the extreme value theorem, it implies that f has global max and min values. It's not so immediate. I mean, the interval is closed, but is the function continuous? Well, it's piecewise. You do have to check whether it is continuous around the number 0, where the break happens, but that is the case, right? What are the two pieces trying to approach as you approach the number x equals 0? Well, the x terms all become 0, and both pieces approach the number -1 as x approaches 0. So you know it is a continuous function. Therefore, you know the global min and max must exist. And we're trying to find it as well as find the critical points. So derivative, first of all. Well, the derivative formula for this function, you can take the derivative of each part separately, but that's only going to be valid in principle in the interior of the corresponding parts. You don't know if that's valid for x equals 0. Notice right here, I have to write larger than 0, even though the original formula was valid for all x including 0. But because the function changes behavior after 0, if you want to find f prime of 0, you need to take a limit of difference quotients. What is f prime of 0? By definition, limit as x approaches 0 of this particular expression, the difference quotient, which we can simplify by knowing the value of f of 0, it's -1. So minus minus 1 is a +1 up here. So this limit, if it exists, it's going to be f prime of 0. If not, then 0 is a critical point because derivative does not exist. How do you find out if this exists or not? Evaluate it from both sides. For example, plus. If you're coming towards 0 from the right side of 0, then the expression for f of x, don't look up here, this is f prime. Look up there, f of x is minus x squared minus 6x minus 1. I forgot the limit symbol here. Pretend the limit symbol isn't there. Okay, so what is this limit going to be? The +1 minus 1 go away. You can cancel 1 power of x after going the 1 and minus 1 going away. So you have limit of minus x minus 6. And it's going to be minus 6. If you compute the other one, similar procedure here. You're going to use the other piece of the function now. You will find -4, I believe. Yeah. No, plus 4. Yeah, the coefficient of x in the other piece. So those are actually different from each other. Therefore, f prime of 0 does not exist. So all of this was to determine the one location where f prime does not exist. It is 0. Does not exist there. 0 is a critical point. Because f prime of 0 does not exist. But now, what about locations where f prime is equal to 0? Those are also called critical points. So let's go back to the formula of f prime. Here it is. These expressions are going to be 0 at certain locations. As long as those locations are agree with where the expressions are valid, you do have these restrictions here, then you can say those would be corresponding critical points. So for example, now, yeah, let's remember this formula. Maybe I copy it down. This is f prime. Let me copy this down. Okay. Let's find where is f prime of x equals 0 now. We'll analyze the two separate pieces. If x is less than 0, then you're trying to solve the equation 2x plus 4 equals 0. X is equal to -2. This is a valid solution. This one really is a point that is less than 0. It is under the restraint, the constraint that you have here. So this is a location where f prime is equal to 0. What about if x is larger than 0, the other piece? Well, then you're looking for solutions to -2x minus 6 equals 0. What is the solution here? X is equal to -3. That one you don't count. -3 is not larger than 0. So when you're doing piecewise functions, be careful with this kind of thing. You want to, the solutions that you find to the where those pieces are equal to 0, they have to be in the correct places. So we only found x equals -2. That concludes our analysis of critical points. 0 was a place where derivative does not exist, and -2 is a place where derivative is 0. So now how do we find global min and max? We already know they exist. They must be one of the endpoints. What were those? If you go back to the function, it was between -4 and 4. So they must be one of the endpoints or the critical points that we just found. Yes, so now you have to go back and evaluate the function at each one of these numbers. Go back to the formula of f and try to do that. You're going to find, if I'm not mistaken, you're going to find these particular numbers, all negative. So the global max value, the largest of all of this, would be -1. It actually happens in 2 different locations. Which, you know, sometimes that happens. The global max value can happen in more than one location. And only one global minimal, -41. This is the answer to the second question. So moving on. Now we're switching topics here. This one is about kind of both now, the extreme value theorem as well as the initial value problems. It's a motion type of problem. So you have a cannonball initially 30 meters above the ground, and it's going to be launched upwards, initial speed of 20, but then it's falling with the acceleration of gravity, constant, equal to 10 meters per second square, directed downwards. So a quick diagram of what's happening. The cannonball initially is 30 meters above the ground, and initially going up with a velocity of 20. So it's going to go up, but then it starts falling back down again, acceleration of 10. So let's say positive direction for height, positive height direction is up. This is really up to you. You can define it to be down as well. So let's call age of t the height function, even before we read what the problem is asking. You know that motion problems, as soon as you have a function representing distance or height or displacement, anything like that, you can start taking derivatives of that and you get functions called velocity and acceleration. So you should always know that v is the derivative of position, height, or whatever, h prime in this case. Acceleration is always the derivative of velocity. This is always the case. So now what are the questions asking? First one, write down and solve the initial value problems for the functions v and h, velocity and height. Let's do that first. So what is the initial value problem for v? Reminder, an initial value problem is something of this form where you give the derivative of the function, it is equal to something, and then you also give me a certain value. V at a specific instant of time is equal to some specific value. In this case, v prime is the acceleration, which is constant equal to 10 downwards. So minus 10. Remember that up is positive, so downwards it would be negative here. V prime is constant equal to negative 10. And what is the only instant in time where we know the velocity? Well, initially it's 20 up. So v of 0 is 20. 0 corresponding to initial time. This is an initial value problem. Let's solve this. From the first equation, always start by solving the first equation. You have this. You're going to integrate. You're going to take an antiderivative of the function that you have on the right side, which in this case is a constant function, just minus 10. So the integral of minus 10 is minus 10t, a function whose derivative is minus 10. And you have to add a c. This is always there if you're finding the general antiderivative, because we don't know yet what this c is going to be. You get that c from the second condition, which is called the initial condition, or initial value. V of 0 is 20. So 20 is equal to what you get by plugging in t equals 0 into this expression. So that's just the value of c in this case. 10 times 0 is 0. So the solution to this initial value problem is minus 10t plus 20. All right, it's still in item A now. We also want to do the same thing for the height function. Write down an initial value problem and solve it. Well, h prime is the velocity, and we just found it. Velocity is minus 10t plus 20. And the only point where we know the value of the height is the initial value. It's 30 meters above ground. So above ground means positive in this case for our convention. This is the initial value problem. Let's solve this. So from the first equation, h is going to be the integral of minus 10t plus 20. How do we do this? Okay, what is the integral of minus 10t? Leave the minus 10 outside of it. Integrate the t function. That's t squared over 2, the power rule. Integral of 20 is 20t. And there is some other value of c here. Maybe call that c2. And how do we find this c2? Use h of 0 equals 30. So plug in 0 for t. You see that once again these terms disappear. This is just equal to the value of c2. By the way, that usually happens when you have things like this, polynomials, and the initial value is always t equals 0. Then that's very easy to find the value of c, because when you plug in 0, everything in here becomes 0. So the c is this value that they gave, this 30. But that's not always the case. So be careful with that. So yeah, we found h. h is equal to minus 10 over 2 is minus 5. Minus 5t squared plus 20t plus c2, which is 30. This is the height function. Let me scroll back up now for item B. B is asking, what is the maximum height reached by the cannonball? How do we answer this question using calculus, using derivatives and everything? Maximum height. This is the height function right here. We just found it. Now we want to find the maximum value that it can have. I mean, the domain for this would be between t equals 0 to infinity. We want the global maximum value of h in the domain between 0 when time starts and technically infinity if you don't know where it's going to stop when the ball reaches the ground. Just imagine this ball is going to keep falling forever. But initially it starts going up. So it goes up, reaches a global max, and then starts going down. We're going to be able to find that global max with the derivative. Well, this derivative is the velocity function. We already found it, but it's very easy to find it again by taking the derivative of h minus 10t plus 20. Always defined. There are no points where the derivative d and e, but it could be a 0 at one location, t equals 2. This is the only critical point. That's what I was just doing here, by the way. Take a derivative, set it equal to 0. That's how you find critical points. So t equals 2 is a critical point. That must be the one that we were looking for. The location where the height becomes maximal and then starts falling again. But what is that height? Well, plug in 2 into the height function. H of 2 is minus 5 times 4 plus 20 times 2 plus 30. I'm looking up here for the height function. So you have minus 20 plus 40 plus 30, that's 50 in units of meters. That must be the maximum height. All right, so this is the problem. If you want to visualize what was happening, the height started with an initial value of 30, and as time goes on, the height starts going up because we shot the cannonball up. It's going to reach a maximum height and then fall technically forever, but yeah, in reality, it would stop here when it reaches the ground. This is the point that we just found with a height of 50. Time equals 2. But that's it for this problem. So we've now transitioned into the topic of antiderivatives. Here's a quick problem about antiderivatives. Calculate an antiderivative of this function. Because they said any specific one will do. We don't technically have to write the plus c in this problem. But we can. We should try to always do that. Okay, what is antiderivative of the function? It means take this procedure of integral. But how does that work? Remember that we do not take the integral of each piece separately, like numerator and denominator. Don't do that. You have to somehow manipulate the function to get something that you recognize. In this case, it's all power rule. Split the fraction, divide each one of these terms by the same denominator. So really it is minus 5/3 x to the minus 2. Yeah, like this. And then you have 2/3 x over x squared is the same as x to the minus 1. Then you have minus 3/3, that is minus 1. The x's go away. And finally, 4/3 x cubed over x squared is just x. How do we integrate each one of these guys now? We're going to use this power rule. Remember, if you want to integrate x to any power other than minus 1, what you do is add 1 to the power and also divide by that same number for r different from minus 1. This is the power rule for integrals. So we're going to do that in here. The constants you leave in front, minus 5/3, for example, leave that. What is x? The integral to the x to the minus 2, that would be x to the minus 1 divided by minus 1. So I'm going to do this for all terms except the second one. This is x to the minus 1 here. The formula would not work, this one. What does work here? What is a function whose derivative is 1 over x? That's the log function. And because you don't know if x is positive or negative, you have to put absolute value inside of x. So ln of absolute value of x, that's the second term. Minus 1, the integral of that is minus x. It follows from the power rule, but it's probably easier to just think, what is the function whose derivative is 1? That's the x function. And then 4/3, let's use the power rule for this x here, which is x to the 1. So you add 1 to the exponent and divide by that same number, x to the 2 over 2. Now let's just simplify this, clean up. You have minus 5/3 divided by minus 1, so 5/3 x minus 1 plus 2/3 ln absolute value x minus x plus 4/3 x squared over 2. I'm not adding the plus c because they said find an antiderivative. So this is it. Next problem. Here's one with trig functions. Yeah, so when you look at this, calculate this integral. What you might think to do is probably something like this. When you first look at this, maybe your practice with limits allows you to see this very quickly. Sine square is 1 minus cosine square. And if you then factor this term 1 minus cosine square as 1 minus cosine times 1 plus cosine, cancel with the numerator. So this function simplifies down to just this. But the integral of that, if you want to integrate now, let's put this integral signs, d theta, d theta, d theta. That's kind of difficult. It's not so easy to find this integral. What is a function whose antiderivative is equal to this? Well, certainly you cannot do this. You cannot split the denominator like that. That's just not true. You can split numerators like this when they have the same denominator, but not the other way. So we don't do that. This simplification is just not helpful for this problem. What is going to help then? Well, look at the original expression. You can split up numerator because you have just one term in the denominator. You can certainly do this. 1 over sine square minus cosine theta divided by sine squared theta. As it turns out, these are both functions that we should recognize. We know that they are derivatives of something. Maybe if we rewrite them, 1 over cosine is the same thing as cosecant. And then here you have a cosine over sine, which is cotangent, times 1 over sine, which is cosecant. Okay, so maybe I'm gonna just include this extra step there so you can see this. Cosine over sine times 1 over sine. So yeah, do you remember now, what is a function whose derivative is cosecant squared? Well, the cotangent function has a derivative of minus cosecant squared. So this one would be minus cotangent. And similarly, the cosecant, the derivative of that is minus cosecant cotangent. So this is the answer, and technically plus c here because they just said find this integral, find this formula. This is the final answer, minus cotangent plus cosecant. So once again, why? Because the derivative of these guys, cotangent, let me write it this way, cotangent prime and cosecant prime, they are minus cosecant square and minus cosecant cotangent. It's useful to have these memorized by now because then you can recognize them when you see them inside of an integral like this. Yeah, so this is the final answer here. If you input this into Wolfram Alpha, for example, or some calculator, they might give you tangent of theta over 2 instead of this expression. They are actually equivalent. It's going to be the same numbers by trigonometric identities. But yeah, if you're gonna give that as your answer, you better have a good explanation why. The explanation being the calculation. But if we do the calculation directly, this is what you get. So let's move on. All right, let's change topic now. Let's go to the L'Hopital rule. Quick reminder, what is the L'Hopital rule? If you have a limit of the form 0 over 0 or infinity over infinity, then it is equal to a limit where you put the primes on the functions as long as this limit exists. This is L'Hopital rule. So just like this first example here, calculate this limit. Doesn't matter where x is going. First of all, check that it is 0 over 0. Plug in x equals 2 in both numerator and denominator. You're going to see they're both 0 and 0 over 0. So you know that you can do L'Hopital. So let's do L'Hopital here. Remember, L'Hopital does not mean taking the derivative of the whole quotient. That's not what you do because that would be quotient rule. It's complicated. We don't do that. It's just derivative of each one separately. So 2x plus 1 in the top, which is very easy. But what about the bottom here? Well, that one requires the chain rule for the square root function. The derivative of square root would be 1 over 2 square root, which you should have memorized by now. You need to multiply this by the derivative of the inner function, 8 minus x squared, which is minus 2x. That's the derivative of the square root term. What about the minus x? Well, that's just minus 1. And suddenly this is something that allows you to plug in x equals 2. You're going to have 5 at the top. And what about the bottom here? You have 1 over 2 times 1. No, sorry, 2. This is 8 minus 4 under square root, so it's 2. Times minus 2 times 2. Minus 1. So that's minus 5 over 2. This is the limit. Because we found a number that exists, that's also equal to the original limit. So very easy. Just be careful with the derivatives. You have to take them correctly. But what about this one now? It is not of a quotient type initially. We have to convert it to that type. But first of all, let's try to think about what's happening. So this limit is of what form? X is going to 0 plus. Sine x is going to 0. And then what's happening to the square root here? Well, if x is going to 0 from the right side, 1 over x is going to become large because x is small and positive. So it's going to plus infinity. Infinity minus 1 is just infinity. Square root of infinity is just infinity. 0 times infinity. That's what I was getting to. A limit of this form is indeterminate. You cannot say it is equal to any particular number. It might be anything. But how do we do this with L'Hopital? Answer is we need to rewrite one of the two functions in the denominator and as a reciprocal. For example, we're going to take the second one. But first, I'm going to just simplify it a little bit so it is of fraction type. So this is the second function that we have. Taking a common denominator in it, it's 1 minus x divided by x. Right, this particular function here, that's what it is. So now, yes, the sign is going to 0. This guy is going to infinity. I'm going to rewrite this guy as a reciprocal of itself in the denominator. Because, well, if the function itself was going to infinity in that case, now the reciprocal of that is going to 0. And now this is of the form 0 over 0. We don't even have to check this again, right? We know this reciprocal. You see that I took the reciprocal inside of the square root, which is how this works. You just know this is going to go to 0 because the original was going to infinity. So 0 over 0, that's something to which you can apply L'Hopital, LH. So we do that. Take the derivatives now. Sine becomes cosine. And this crazy square root, what is it going to become? Well, derivative of the square root, 1 over 2 times the same square root, times derivative of the inner function, quotient rule. So we're gonna do low d high minus high d low over low square. Looks more complicated. Usually, I mean, I don't know about usually, but sometimes it actually is more complicated. But the point is that usually it's going to be something that allows you to plug in 0 now. It's not indeterminate form anymore. Just check it out. Plug in 0, you have cosine of 0, which is 1, divided by 1 over 2 square root of, well, actually, that's, yeah, because I don't want to write 0 in the denominator twice. Forget about this. Let's actually simplify the function first. That's, by the way, a good idea. Before plugging in, I just recognized this square root would give me a 0 in a denominator. That's bad. But this denominator is the denominator of some larger fraction itself. So let's simplify first. What do we have here? Okay, cosine x divided by, let's leave this as 1 over 2. You have 1 over the square root. So you can write that as the square root with the reciprocal inside. And then what is this big fraction? You see that you have a minus x and a plus x. Those are going to go away. Like this. And now I can move everything that's a double denominator to the top. Like the number 2. This square root of x. And this 1 minus x squared. Everything in the top. Meanwhile, the only thing left in the denominator of the big fraction is this root 1 minus x. Okay, that's better now. There is even a simplification that you could do here if you wanted, but now that's not needed. Trying to plug in x equals 0 will be very easy. 2 times 1 times 0 times 1 divided by 1. In other words, 0. Yeah, so lesson here, after taking L'Hopital, maybe simplify the function that you get. Sometimes you're going to need L'Hopital once again. But before you try L'Hopital once again, try to simplify as much as possible. Or in this case, we needed to do that before plugging in 0. Moving on. Here's a different one where you have tower function, x in the base and also in the exponent. Calculate this limit L. Suggestion, calculate ln of L first. Okay, let's do that. So when you take ln of a limit, you just take ln inside of the limit. You take ln of the expression itself. Sine x to the x. Why are we doing that? Because the ln brings the exponent down. It becomes x times ln sine x. Okay, now we check. What kind of limit is this? X is going to 0. So this x is a 0. And then times sine x goes to 0. And then ln of 0, what is that? Well, that's minus infinity. As x approaches 0 from the right, which is the case here, ln x is going to minus infinity. So once again, we have a limit of the type 0 times infinity. L'Hopital cannot be applied directly to this. You have to transform this into a quotient first by moving one of the two functions to the denominator. Always choose the simplest one, in this case the x function. So I'm going to rewrite this with keeping the ln upstairs, but moving the x downstairs as a 1 over x. This is the same function as before, but now it is of the form minus infinity over infinity, which is a form that allows L'Hopital to be used. So we do that. By L'Hopital, what does this become? All right, the limit, the derivative of ln of sine, you have 1 over sine for the ln part, and the derivative of sine is cosine. This was the chain rule. Meanwhile, the derivative of 1 over x is minus 1 over x squared. So simplifying this, in other words, moving the x squared to the numerator, you're going to have cosine x times x squared divided by sine x. Okay, very good. What do we do with this? Well, if you try to plug in x equals 0, you're still going to see a 0 over 0 because of the x squared and because of the sine. So it is 0 over 0. You can try L'Hopital, but the point is there are certain things, certain parts of the function that are not contributing to this 0 over 0, namely the cosine or even the minus sign in front. It's okay to bring those outside. It's okay to do this limit of minus cosine times limit just of the problematic part, sine the x squared over sine x. Limit of the product is product of the limits as long as both exist. So as long as we can find answers in here, and we will, then this is justified. So the reason to do that is that this is going to simplify your L'Hopital now. When this is the 0 over 0 part, it's much simpler to take derivatives here. Whereas with the cosine in it, it still would work, but it's just more calculations to be done. All right, so simplify it like this first, and now apply L'Hopital. So, well, L'Hopital is only applied on the second one, right? That's the 0 over 0. This one is just minus 1. Cosine of 0 is 1. Now the second part becomes, by L'Hopital, 2x over cosine x. And what is that now when x is going to 0? Well, 0 over 1, that's 0. This is the answer. Well, let me take that back. This is not the answer yet. This is the answer to the limit that we just found. Go back through all your calculations. That was ln of L. It was not the original limit L, it was ln of it. Then what is L? Well, take exponentials here. L is 1. That's better. So don't forget this last step. When we're dealing with tower functions like this, this limit is equal to 1. Okay, and then finally, this is just an application of L'Hopital. It allows you to compare functions. A question might be asking you precisely this. You don't see a limit being asked here, but this is what they are secretly asking for. The problem is, as x grows large, which function becomes larger, x or ln x squared? So what they are asking for is this. As x grows large, so we're going to take x to infinity, which one of the two functions is larger? So compare the two of them by dividing one by the other and see what happens. If you find infinity, for example, here, that means the fraction is big. It's getting big, which means the numerator is larger, x is larger. Or on the other hand, if you find a 0, that means the whole fraction is small. And why is that happening? Because the denominator is the large part, is the dominating part. So we have to verify which one of these is going to win. And you probably should remember, logarithms, they grow very slowly. Even with the square on it, even with any power that you'd like here, the x function is actually gonna grow larger. And we're gonna see that. So let's find this limit here. This is infinity over infinity. Because x is going to infinity, both of these terms go to infinity. So you can do L'Hopital. Take derivatives. x becomes 1. What about ln x squared? The derivative of the square function would be 2 ln x, and the derivative of the ln is 1 over x. Okay, simplify this. Take the x from the denominator. Sorry, the 1 over x. This is the simplification of the function. This is still of the form infinity over infinity. So do L'Hopital once more. Derivatives. Derivative of x is 1. Derivative of 2 ln x is 2 over x. Simplify this. This is the same thing as x over 2. And now finally, this limit is infinity. So once again, what does this answer tell us about the original fraction? If the original fraction has a limit of infinity, which means it's very large, the only reason for that is because the numerator dominates over the denominator. So x becomes larger than ln x squared. You might have tried to compare the functions in a different order. You might have tried ln x squared over x, so the reciprocal of that, and you would find an answer of 0, which still supports the same conclusion. As long as your conclusion is right, that's how you do the problem. So I have another one similar to this, and then we're done. We're trying to compare once again two functions, f and g, and we're letting a number x larger than 1 approach the number 1. Which one becomes smaller this time? So in other words, we want to let x approach 1 from the right because they said x is larger than 1. And let's say we compare f to g. So let's say we try to evaluate this limit, ln x over e to the x minus 1 minus 1. Okay, we'll draw conclusions when we get to the answer. Plug in 1 first of all. Ln of 1 is 0. E to the 1 minus 1 is e to the 0, which is 1. Then there's another minus 1 there, making that also a 0. 0 over 0, L'Hopital. You have to check first of all before you do L'Hopital. But okay, what do you get here? Derivative of ln is 1 over x. Derivative of the exponential function. Chain rule here, although it doesn't really affect anything. Outer function is the exponential, so e to the x minus 1, times derivative of the inner function, x minus 1, that is a 1. And finally, this minus 1 does not contribute to the derivative. So this is the derivative right here. Now what happens when you plug in 1? 1 over 1 divided by e to the 1 minus 1. This is 1. What does this answer mean? We did not find infinity or 0. We found the number 1. Okay, this means the fraction is approaching the number 1 as x grows close to 1. That means the two numbers are comparable in size. Because if the fraction is very close to 1, then both numerator and denominator are close to each other. So which function becomes smaller compared to the other? The answer is none. F is actually, you can say, for example, has comparable size. To G. I mean, the question is not really well phrased. Probably a book problem or an exam problem will be more precise about what they mean. The question really doesn't mean to say which function is larger than the other, like f is larger than g or vice versa. They're trying to say as comparable sizes. Is one of them very much larger than the other, or do they have comparable sizes? And the answer was the second option, because we found the number 1 here. So yeah, we can do L'Hopital. We can apply L'Hopital to things like this, where we compare one function to another. But I think that's going to be it for this review.